Okay, so thank you to Professor Oz. So we are going to skip the opening remarks by Professor Ben Israel because apparently he's not here yet. Maybe we'll do it later. So I'm very happy to invite my friend, Professor Wolfgang Schleich from Ulm University, to give the first guest lecture. So Wolfgang, please.
So, good morning, everyone. It's a great pleasure to be here. And we're all fascinated by quantum mechanics, and in particular by using atoms, cold atoms, to probe the interface between quantum mechanics and gravity. This is the topic I have chosen for this talk today. The question is, can we learn anything bringing together quantum mechanics and gravity? Now, you might know that so far we don't have a theory of quantum gravity. We have various versions of it, but it's not easy to quantize gravity. And I remember a quote from Bryce DeWitt, one of the big heroes of quantum gravity. He told me once that when he was a student at Princeton, Wolfgang Pauli came into his office, looked over his shoulder and said, "What are you working on, young man?" And he said, Bryce DeWitt said, "Oh, I'm trying to quantize gravity." And Pauli looked at him and said, "Well, it will take a real smart man one day to do it," and walked out. So, and Bryce DeWitt told me, he said, "Look, and we still don't have it." Now, of course, I'm not going to develop it in here either, but I want to show you some ideas and experiments mainly, that work on this interface of gravity and quantum. I am at the University of Ulm. You see on the left-hand side a picture of our cathedral, which for many centuries, one can say almost, had the highest church tower in the world. It was taken over now by the church in Barcelona. It's about 10 meters tall, taller than Ulm. And you see it here coming out of the fog, sticking out of the fog. And what you see in the very end, in the very back there, are not clouds. These are the Bavarian Alps that you can see from almost my office in the November. I have a part-time job at Texas A&M, and enjoy working there with a quantum physicist. So what I will do is I will start out from the equivalence principle. And you will see there are various, and most of you know there are various versions of the equivalence principle. I will then talk about matter waves and how matter waves allow us, using interferometry with matter waves, to probe the equivalence principle in various versions. And then at the end, we will talk about no gravity or almost no gravity cold atoms in microgravity and what it is that we can learn from there. As I said, I will report a lot about experiments, and of course I'm a theorist, so I had the great pleasure to provide the theoretical background for these experiments, but the experiments were under the leadership of Professor Ernst Maria Rasel from the University of Hanover, and we have worked together very closely over the last decades. Let me start out with a picture from Ulm. On the left-hand side, this building was a building very close to the railroad station in Ulm, and the gentleman on the right-hand side, Albert Einstein, was born here in 1879. He left very early in his life, moved to Munich and of course other places, but at least we can claim in Ulm that he was born, even if he left very early. By the way, when I was hired, just a little joke on the side, when I was hired at the University of Ulm, the professor who hired me was Professor Hans Riskin. He wrote a famous book on Fokker-Planck equations, was a very famous man in laser theory. He once said, all the people who became famous left Ulm very early on. Herbert von Karajan, Einstein. He says, your career is finished already, you came here. But anyways, so Einstein, when he was in his patent office, said, and this is a very famous quote, I was sitting on a chair in my patent office in Bern, and suddenly a thought struck me. If a man falls freely, he would not feel his weight. I was taken aback. This simple thought experiment made a deep impression on me, and it led me to the theory of gravity. So what is this all about? Of course, we know from the weak equivalence principle, and of course Galileo, who dropped, according to the rumors, dropped objects from the Leaning Tower in Pisa, he found out that these objects really fall with the same rate no matter what the substance is. Now, if you have a constant electric field, as indicated here in the very top, a constant electric field and a particle with a charge, the inertial mass, mi, of course, depends on the ratio of the charge and the inertial mass. However, if you're in gravity, then because the inertial mass is equivalent to the gravitational mass, the two masses drop out and the acceleration is independent of the mass and only depends on the acceleration, g. So that is exactly this observation that Einstein made, namely that the masses drop out of the equations and everything falls with the same rate. You don't feel gravity when you're in free fall, at least not till you hit the ground. So the weak equivalence principle, by the way, is not something that Einstein discovered. Already Heinrich Hertz, who developed the radio waves, Heinrich Hertz already was aware of this fact. Of course, as I said, Galileo too. But Heinrich Hertz wondered already, where is this principle coming from? He didn't have an answer, but he was very deeply fascinated by this question too. John Archibald Wheeler, whom you see here sitting on his island in Maine, and he wrote a beautiful book, of course, on gravity. This is the famous book, Misner-Thorn and Wheeler, Gravitation. But he also wrote a very nice book, A Journey into Gravity and Space-Time, in which he explains, essentially without equations, what gravity is all about. He even explains the Schwarzschild metric without going into deep equations. And the key idea that we take off his observation, Einstein's observation of the weak equivalence principle, is that if you have gravity indicated here by a mass distribution, and you have a house here, and you look at the trajectory of a ball, you're going to see the curvature due to gravity. However, if this part here breaks and the house is falling freely, of course, this trajectory is now a geodesic. So it's transformation of coordinates that is important and which leads us eventually to another version of the equivalence principle, and that's called the Einstein equivalence principle, which says that all physics is the same in every coordinate system. So if I look at quantum mechanics, I look at thermodynamics, I look at electrodynamics, I could formulate these theories in a so-called covariant form so that I will see that the equations always take the same form. They are always taking the same form, no matter in which coordinate system, freely falling or accelerated frame, it's always the same. And this is something that we probe now with Ron Folman from Ben-Gurion University, and I will come to this in the talk. The strong equivalence principle is one step further. When I made this list of theories that you can compare to, I did not mention gravity. So the strong equivalence principle is one step further, where you now also say gravity behaves in the same way as electromagnetism when you transform it from one coordinate system to the other, or gravity is the same in all coordinate systems. Now, we are probing it with an observation that was made in 1924 by Louis de Broglie in his PhD thesis. He had the idea that matter will also behave in the same way as light. It will show wave properties. Einstein, by the way, was a referee of that thesis. And very shortly after this, Davidson and Germer in America found that when they bombarded a nickel crystal with electrons, that they could see a diffraction pattern similar to that of light. Now, I recommend to you to look at the original paper by Davidson and Germer, because there they confess how they made this observation by accident. What had happened is a valve had blown up. Oxygen got onto the crystal and oxidated it. And it's because of that that they saw the effect. So if you read the original paper, it's very interesting to see they confess that they were looking for the effect, but they only found it because of an accident in the laboratory. So here, of course, and it was already mentioned, that Schrödinger is the man who put these waves of our friend Louis de Broglie into a form of a wave equation. There's also a very interesting historic part to it. Schrödinger was a professor at the university in Zurich, and Professor Peter de Baye was the big, we call it nowadays, mucky-muck in a technique at the ETH in Zurich. And he once said to Schrödinger, hey, you're not doing something interesting. Why don't you give a talk in the colloquium on the theory of de Broglie? As I said, you know, anybody who knows German professors would understand that Schrödinger should have been pissed. But anyways, he gave the talk, and after the talk, de Broglie said, hey, if that's true what you're saying, there must be a wave equation behind it. Why don't you go and find the wave equation? And Schrödinger found the wave equation. He gave a colloquium about a couple of months later in which he described this wave equation. And this is the fourth paper of a series of papers by Schrödinger called Quantization as an Eigenvalue Problem. In the first paper, he solved the hydrogen atom. He wrote down the time-independent Schrödinger equation, solved for the hydrogen atom. And then on the fourth paper, he finally addressed the question of the time-dependent Schrödinger equation. And he kind of did not, of course, derive it. He guessed it. He had about 3 or 4 different versions. And the one that we eventually today appreciate and like is this equation, as you see here. And because he took the square root of another equation that was a 4th order in space and 2nd order in time, that's why he suddenly found the plus and the minus sign here. And as I said, this is the original paper here, and I just amplified the equation. So this ambiguity in the sign was there already in the original paper. So the first group of people who combined gravity and wave nature of particles were these 3 gentlemen here, Overhauser, Albert Overhauser, Robert Colella, and Sam Werner. They used a silicon crystal and created 3 crystal lattices here and sent in a neutron, and the Bragg scattering from these periodic potentials, if you want, and periodic potentials are important in a second in the optical version of this experiment. These diffracted the neutron beam in a coherent way into 2 paths. The next lattice did the same, and then, of course, due to the second one, you have like a mirror, and it brings the beams back here. You mix it again, and the 3 counters back there count now the neutron going on this path and on this path. And as you now rotate this interferometer with respect to this axis, you will see a fringe change. And gravity points downwards here. And the phase shift depends on the area that is enclosed by the 2 paths. And as a result, you're going to see a modulation as you change the angle of this interferometer with respect to gravity. I said we translate this experiment with neutrons and the silicon crystal into a light crystal and an atomic beam. And this is something that Mark Kasovich and Steve Chu did 25 years ago. So here's an atomic beam. You have 2 light fields, and these 2 light fields split, redirect, and recombine these atomic beams. So essentially what you have is you have a trap with the atoms, and then you have these what are called Raman beams, where you transfer momentum onto the atomic beam so that you get a coherent splitting of these two atomic beams. And if you change the phase of one of these waves, then you're going to see a count rate, a change in the count rate that is periodic, very much like what I showed you in the case of the neutron beams. Weak equivalence principle. The experiment here by Ernst Rasel showed that you can take such a Mach-Zehnder or Kasevich-Chu interferometer where you have 3 pulses, and now this is time, and this is the coordinate in long of gravity. You can now impart momentum to these 2 atoms. We used potassium and rubidium, and you will open 2 types of interferometers, one for potassium, one for rubidium, and you can look at the fringes that you can see, and I don't want to go into the details of the picture. It suffices to say that you can measure now with 2 species and the wave nature of the 2 species, the weak equivalence principle. Now you might say, well, how good is this experiment compared to Eric Adelberger's experiment in Seattle, where you use the old Cavendish experiment type, where you have 2 masses on a torsion pendulum. And of course, we are embarrassed to say we cannot compete with these type of experiments, but what it is here is really that we're using the wave nature and not Newton's equations of motion to test this. Now, why and what are the properties of this Kasevich-Chu interferometer? There was a debate a couple of years ago about, can I measure the gravitational redshift with such an interferometer? And there was a big debate, and our resolution was no, because such an interferometer measures the acceleration, not the redshift. Now, I don't want to go into the details, but I want to draw the effect, I want to draw your interest in this phenomenon in a different way. So here I have again plotted gravity downwards, the coordinate along gravity, and I have time in this direction. We have 3 laser pulses separated by a time t, and so the atom comes in here, feels gravity and falls down, provided it has not interacted with the light field here. If the atom has interacted with the light field, it feels a momentum and it runs up against gravity. Now here, this laser pulse inverts excited and ground state atom. So now this atom in blue is in the ground state, whereas this atom now is in the excited state, and the third one, as you can see, mixes the situation. Why am I showing you this? Because you see that there's a time ordering. On this path, the atom is first in the excited state, then in the ground state, whereas on this one, it's first in the ground state and then in the excited state. So this phase shift here in the end, in some sense, measures the difference in the time ordering of the events. If you translate this into mathematics, you have one Hamiltonian in which you have the kinetic energy plus linear gravity. In the other Hamiltonian, you have the kinetic energy given by the momentum plus the h bar k. And you can immediately see that they don't commute. These 2 operators don't commute. Why? Because there's a cross term here between this, because of the square, and it's proportional to p. And of course, p doesn't commute with z, and as a result, you're going to measure the acceleration. Now, another important insight from that is, since you measure the time ordering of these 2 procedures here, excited and ground state, excited state, the phase shift that you must observe in such an interferometer scales with the square of the time between here and here. So it's quadratic in time. Why? Because if you have a unitary time evolution, each Hamiltonian is multiplied by time due to the Schrödinger equation. So if you look at the commutation relation between the 2 and the phase shift here, it must be quadratic. So as you increase the time of the atom spending in the interferometer, your signal will go up. So it's very important to have large times for the atoms in the interferometer. Now, atoms feel gravity. And therefore, the atoms, if you slow them down, eventually they will just feel gravity and fall down. And so what you want to do is you want to have very slow atoms, but you don't want to have really gravity there. This is why we eventually will go to microgravity to do these experiments. Now, one way out here was already offered many years ago in the very early days of quantum mechanics by two gentlemen, Kennard and Darwin. They, about the same time, looked at the following problem. You take a Gaussian wave packet that is sliding down in a linear potential. What they found is an expression that you see here out of Darwin's paper, but I want to draw attention to this term here that is linear here in time, and here you see is another term, quadratic in time. So, moreover, g, the gravitational acceleration, appears quadratically here. So essentially you have a term mass times the square of the acceleration times t cubed. I just told you that the Mach 10 interferometer scales like t squared. So the question was, can you build a new type of atom interferometer that uses the scaling of t cubed? Now, in these papers, both of them mentioned that this phase is unimportant because it does not depend on the coordinate. It is what people would call an overall phase that separates out. And indeed, of course, in the Kasevich-2 interferometer, this phase cancels out because the phase shift in both paths are identical. However, we were intrigued by this very much, and in the labs of Lev Shemer here at Tel Aviv University with Adi, and the big hero, of course, is this gentleman here, Gary Roseman, a graduate student at the time of Adi and Lev. He did the experiments with the big water canal here, where we took advantage of the fact that the amplitude of a water wave satisfies the same equation as quantum mechanics, or the Schrödinger equation, except that time and coordinates are interchanged. Now, the first derivative with respect to time in Schrödinger is first derivative in space. Second derivative in time is replaced by second derivative in space. So with this, we could measure this cubic phase that was predicted, because water waves, of course, you can measure phases without any problems, not in quantum mechanics. Now, the question was, of course, can you build an interferometer from it? Now, and what would this interferometer be sensitive to? So you wouldn't believe the conversations we had at lunch in my institute, where I proposed to build such an interferometer. And my simple idea was that we have an atom in a trap. We excite the atom and give it a momentum kick. But now it's in a different state, and the atom would not be trapped in the trap because it's in a different state. So it would fly up, and then it would come back, and so this wave packet would experience gravity. The wave packet that sits in the trap would not experience gravity, and if you have a pulse, send it up and send it down, and then overlap it, you must see this phase of Kennard/Darwin. People said, that's not going to work, and Professor Ernst Maria Rasel, my big hero in experimental physics, said, that experiment can't be done, it has to be done differently. So we came up with a 4-pulse sequence, and here you see the 4 pulses. And of course, this interferometer must be sensitive to accelerations now, because you remember the square of the acceleration appears in the formula of Kennard and Darwin. So what we do is we expose the atom to 2 different accelerations, and then we interchange the 2 accelerations and exchange them again. And we have a pi over 2, pi over 2 arrangements, which means we split the beam. We have kind of like a mirror, we have another mirror, and we have another beam splitter. Now, and you notice, here is the same Werner that I mentioned earlier, Colella, Overhauser, and Werner. It was Sam Werner who pointed out to me one time that there is this cubic phase in the problem, and he said, look, why don't you think about it? And as I said, this is the consequence of it. And Ron Folman in Ben Gurion did an experiment with the Stern-Gerlach matter wave interferometer, and it suffices to say, here you see this cubic phase in the Stern-Gerlach interferometer, and as I said, this is an experimental data, and you see also the scaling that is superior now here in a T cube versus a T squared interferometer. I mentioned this crazy idea of taking the atom in the cavity, in a trap, and then throwing part of it up and catching it again, where Ernst said it can never be done. This is a paper that we did with Ron just recently, and various groups are involved here. And you see, here is height, coordinate, here is time, here is the pulse. You throw the atom up, it undergoes some parabolic trajectory, and here is the reference wave packet, and it stays here on the same height because it's in the trap. And then you recombine it. Now, why am I so excited about it? Here you see the cubic phase again. You see the chip going up. Why is this so interesting? You remember I mentioned Einstein's equivalence principle at the very beginning. The Einstein equivalence principle says that the laws of physics are the same in every coordinate system. Well, we understand in Kasevich-2, we can test that because we have these laser pulses, and when you analyze a Mach 10 interferometer, or I should rather say Kasevich-2, in one coordinate system, namely in the lab frame, and also do it in the frame of the atoms, what you find is that the phase shift, of course, must be the same because the phase is an invariant, but what you find is that it's only invariant because now the light field has changed its frequency. Because you're accelerated from the atom, it falls down and it sees a light field, and it gets accelerated as it sees a plane wave, and therefore the frequency gets chirped. And that's what you see in the phase shift. Now here, in the experiment with Ron Folman, for the first time, and this is why I'm excited, we see a symmetry in the matter waves. No matter in which frame you are, you always get the same phase shift, and there are no electromagnetic fields involved. It's because the Schrödinger equation, I'm not saying is Galilei invariant, it's not true, it's not Galilei invariant, but you get the same phase shift in both coordinate systems, and you're only comparing matter waves. Bose-Einstein condensates, so far we have talked mainly about cold atoms, but not necessarily Bose-Einstein condensates. Here is the original paper by Einstein, and down there is how he submitted the original manuscript, not in Tech, obviously. And you notice, even as he was working on it, he added remarks. In particular, here he said, von Herrn Bose erhalten, oder erdachten Betrachtungen. And so Bose was, of course, in India, and at that time, almost exclusively, physics was published in German. And so Bose had discovered the statistics, and he wanted to make sure that it's noticed, and so he sent this paper to Einstein and said, can you please translate it into German for me and submit it? And this is why Einstein put this in, but as Einstein was reading the paper, he got some new ideas on it and did his own paper. But as you notice, he gave credit to Bose. Now, here is the first experiment, got the Nobel Prize of the group in Boulder, the rubidium condensate, and you see as you decrease the temperature of the atoms in the trap, you see the emergence of this peak here, and this is the peak arising from more and more atoms going into the same quantum state of zero momentum. How do you see this here in the experiment? This is a picture taken after you release the atoms from the trap. So you open the trap, the atoms are running out because they have some kinetic energy, and then you take after a certain time a picture of this, and you see how far the atoms have moved. And how far they have moved is a measure of the velocity. So if all the atoms stay together, then you're going to see this peak here, because now they must have had a very, very low velocity. Now, many years ago, about 10, 15 years ago, we were approached, is it possible to do such a condensate in microgravity? Now, at that time, we couldn't go to the International Space Station, but we found a friend of mine, Professor Hans-Jörg Dittus. He had built this tower in Bremen. And you can drop objects in here, and you have about 4 seconds to do an experiment on these objects before they hit the ground. So here is a cut through this tower. So you see you have about 120 meters, and there's a capsule here on the top, a release mechanism, and the whole thing falls down. And there's a pile of styrofoam, just styrofoam, to decelerate these capsule. You can also have a catapult experiment where you shoot up on a parabolic trajectory and a capsule, and you catch it again here with this. And in the end, you have 9 seconds. So 15 years ago, we could do the experiment, essentially thanks to Jakob Reichel and Ted Hensch, who had developed a new type of trap which allowed us to miniaturize the whole experiment that usually is on a laser table, a big laser table of mirrors and lasers and vacuum chambers. And now one could put this whole experiment into a capsule of 2 meters times, 82 centimeters. And the chip developed by Hensch and Reichel, and of course also by Ron Foreman in Ben Gurion, is a chip in which you have wires on here, and these wires have currents. The currents create magnetic fields, and the magnetic fields attach, I shouldn't say attach, but keep an atom with a magnetic moment in free float. So that's how you trap these atoms, because you have these magnetic fields and magnetic moments of the atoms. Then you shine a laser on it, and you can see the distribution of atoms. And this here is the first Bose-Einstein condensate created in microgravity in free fall. So what happens is you have this capsule, you release it, and while the capsule is falling down, you're preparing the atoms, you're making the measurement, you let it expand. And then you, of course, catch the capsule at the very bottom. Atom interferometry. Can you do atom interferometry? Yes. We did this also here in the drop tower. Now the experiment is much more complicated, because you have to start from the MOT, you have to put it into a Joffe-Pritchard trap, you have to create the Bose-Einstein condensate, you have to cool it, with a delta cooling mechanism that I don't want to deal with right now. And then you have only from 2.7 seconds to 4.5 seconds time to do the experiment, the interferometry, and then the imaging before you hit the ground. And here is a picture of the interference fringes observed in this particular experiment, as I said, with Ernst. We got very ambitious. We wanted to go to space. As I said, atoms feel gravity. But we want to really do an experiment like an equivalence principle, weak equivalence principle of different masses, different atoms. And we wanted to have very long interrogation times. So we said, okay, let's go away from that and go into space. We're not, Germany doesn't have an international space station, but we have rockets. And these rockets came from Brazil, amazingly enough. And so we got a rocket, and the project was called Maius. And so now this whole device was put into a rocket of about, well, the rocket itself is about 12 meters, but the available space is about 3 meters and 50 centimeters, where you have to put batteries, electronics, and the rest. It was launched in 2017 on January 23rd. Quite an event. It comes out of a bunker, and here you see the fire from the rocket coming out. And so we did, for the first time, a Bose-Einstein condensate in outer space. Now, how do you define space? It's above 100 kilometers. So this rocket was flying out to about a maximum of 200 kilometers, and it had a flying time of about 6 minutes. And during these 6 minutes, we did many experiments. Here you see the typical picture of a Bose-Einstein condensate with the background and this sharp peak that I explained earlier in the connection with earlier in the connection of the rubidium Bose-Einstein condensate from Boulder. We also were able to see fringes of this condensate as indicated here, which shows that these are not just a bunch of atoms, incoherent bunch of atoms, but coherent ones, that they really are a condensate, all the atoms in one particular state of the motion. We could also see and do Stern-Gerlach interferometry, and as I said, I don't want to go into the details here, but rather say, okay, eventually we had proven in Germany that we can handle atoms in microgravity, and of course there was now a development in America to prepare and build a device for the International Space Station. And when I heard of this, I immediately talked to my friends in America, and I said, look, we have all the experience in this business, let us participate in it. And they said, well, you're not going to get any money. And we said, look, that's not a problem because we get the money from Germany, but we want to have access to it. And so, well, the Americans were very kind. The first experiment on the International Space Station was here, published here in June 2020 under the leadership of Rob Thompson and David Eveline. They have seen for the first time on the International Space Station the same transition as you decrease the temperature into a very, very narrow peak, as indicated here. As I said, we, together with Nick Bigelow from the University of Rochester and Ernst, we did experiments now on the International Space Station, and I mentioned delta kick cooling earlier already, where we achieved picokelvin energy scales with these atoms on the space station. And amazingly enough, my students in theory, Matthias Meister, who is now the head of the German Aerospace Center theory department in Ulm, he is doing experiments up there, telling the people at Jet Propulsion Laboratory, what should be the currents, what should be the voltages, and so forth, to do a certain type of experiments. One thing I wanted to mention, as I said, we want to do experiments with different type of masses, different substances, like rubidium and potassium. And 2 years ago, we were able, or the group was able, here you see Rob Thompson, Jason Williams, Nathan Elliott is one of the big heroes in there. We were able to create, on the International Space Station, Bose-Einstein condensates of rubidium and potassium. And here you see the device. It's a very small box, really. You see the astronaut here, the hair at least of the astronaut. You see the legs, so you have a feeling it's not a really big device. And this is all that is needed here in order to do the experiment. So with this, I want to conclude. I hope I haven't taken up too much time. And I talked about the equivalence principle and why atoms, cold atoms, would be interesting to use as probes of this interface of gravity and quantum. We use the wave nature of matter. And as I said, we have done, in my opinion, exciting experiments in microgravity with cold atoms. And I thank the organizers for inviting me here, and I look forward to discussion and questions. Thank you very much.
Okay, thank you, Wolfgang, for this really beautiful work, and we really appreciate that you gave experimental works. You presented experiments, although, Wolfgang is a professor of theoretical physics.
Yeah, and I can show you more equations than you want to see.
Okay. Okay, so we have time for a few questions. Yaron?
That's right. But if you ask me these numbers, I don't remember, but it's amazingly small. Okay, it's amazingly small, and as I said, all of these experiments came from Eric Adelberger and the Cavendish, the torsion balance. Okay, and as I said, we cannot compete with this. There's no way. But the point is, the system is very different. That's why we are so interested. Thank you. Yeah. So now, that's also a very good question. Now, most of these experiments that I mentioned here are just adding a gravitational field to the Schrödinger equation. So we are not really yet in what you said, gravity, quantum mechanics in curved space-time. Now, one thing I did not mention in this context are some experiments that we have also done with water waves, where you really see Hawking radiation in water waves, and in a really beautiful way. So it's very similar to exactly what you say, Schrödinger equation in curved space-time. But I don't want to spend too much time on it, but if you want, there was a paper in Nature Communications, and I can tell it was rejected by Nature because they said it will not attract any attention. This paper, published last year, had over 100,000 downloads. So that tells you something about the judgment in Nature.
Okay, any more questions? Yes, please.
That's a good question. I think it all depends on what type of quantum computer. If you work on ion traps, I don't think it would, because they're levitated. Okay, so I don't think that would help you. If you do a solid state device, I don't think it will help you. Now, what's interesting in quantum computing is there was an experiment by Philipp Walter at the University in Vienna, where they used, I think, photonic devices, and they got a satellite, and they put it into space. And so they have, I don't know, 2 or 3 photonic qubits in space now, and they're doing experiments with it. So they claim it's the first quantum computer in space. I don't know if this paper is published or not yet, but Philip told me about these experiments a couple of weeks ago. As I said, yes, you could. That's what he says, but that's why we are doing the atoms in space, okay? Because we don't, if you want, of course, people could criticize why are you doing all these complicated experiments when you can just levitate atoms in traps. But of course, once you levitate them, you have magnetic fields, and they change the internal nature of the atom. And so that's why we want to do it really in space. And of course, gravitational, there's even a proposal by gravitational wave detection by Kasevich, and they're pushing this very hard, and now also Ernst Rasel is pushing very hard that we just use not mirrors hanging up from the ceiling. And this is how gravitational waves detected nowadays. You have a mirror hanging from the ceiling, and you look at the reflection of the light from it, and you measure the length change. Now, if you look very carefully at the theory, you will see that gravitational waves are detected by the geodesic deviation. Geodesic deviation means freely falling trajectories at 2 different points. Now, of course, these mirrors are not freely falling. But if you would take atoms and you put them into space, they are freely falling. They are not attached to anything anymore. So you could really test gravitational waves by atoms, a bunch of atoms in space, one here and one here, and sending light signals back and forth. So I hope maybe this clarified it a little bit better.
Okay, so thank you very much.
Thank you.